From the study of capacitance, you will recall that a capacitor stores electricity. From the study of inductance, you know that an inductor reacts against any change of current flow. Resistance is always present in both capacitors and inductors. Combinations of resistance, capacitance, and inductance are very widely used in radio apparatus. To understand how capacitors work in combination with inductors, it is important first to understand the effect of a capacitor upon an alternating current. You will remember that when an EMF is impressed across a condenser and resistance in series, a large current flows at first, gradually diminishing toward zero value as the full charge is reached. You will also remember that when a fully charged condenser is short-circuited through a small resistance, a very heavy current flows immediately, the amount gradually decreasing as the condenser is drained of its charge. You can see, as shown by these graphs, that at a given time after the beginning of a charge or a discharge, an equal current will be flowing in each case. If the polarity of a charging source, perhaps a battery, were reversed, instead of merely discharging a charged condenser by a short circuit, the so-called charge and discharge currents would be identical in value, but exactly opposite in direction. They can be thought of conveniently as recharge currents. It is convenient to think of each curve as a recharge curve when dealing with any alternating current, and to represent a recharge current in one direction in the normal manner. The recharge curve in the opposite direction can then be represented by turning the graph upside down. Direction of the current can be further distinguished by labeling the one way plus and the other way minus. The time axis can be designated as 0, since it is halfway between the largest values of plus and minus. Then a graph depicting a series of reversals would develop alternately above the time axis and below the time axis. Such a graph shows both intensity of current and direction of current flow. Current in relation to time can thus be pictured. The plus and minus signs can also indicate voltage changes, in which case the terms plus and minus correspond to positive and negative. For instance, on this graph is shown the battery voltage, which has caused this square-shaped wave by its periodic reversal. Voltage in relation to time can thus be pictured. By design or accident, all AC circuits contain resistance. You will remember that because of this resistance, the voltage as measured across the terminals of a condenser increases as the current decreases. Also, that when the condenser voltage reaches a value equal to that of the battery EMF, no further current flows. This condition can be pictured on a graph. As the voltage increases, the current decreases until it finally no longer flows. On a graph of the battery voltage at a point marked X, a condition may be assumed when the voltage is still positive but about to reverse. On the current curve, the current is then reached practically 0. On the curve of the condenser voltage, the voltage has reached a value substantially equal to the battery EMF. Then, when the battery voltage is reversed, a heavy current immediately flows in the opposite direction. The voltage across the condenser, however, requires time to adjust itself to a negative value because of the resistance in the circuit. Thus, for a period of time following each reversal, a condition exists where the current has changed direction and is in the negative or minus section, while the voltage is still in the positive or plus section. At point Y, the opposite condition exists, and the current is positive while the voltage is negative. You can say, therefore, that in a circuit consisting of capacitance and resistance, the current and voltage are not in step, and that the current leads the voltage. Also, in a circuit containing inductance and resistance, the current and voltage are not quite in step. Over the graph of alternating battery voltage, there is superimposed the curve which the current takes due to the reactance of the inductor. Again, periods are found when the voltage and current are on opposite sides of the zero line. In this case, however, the current lags behind the voltage which produces it. A quickly reversible battery has been used to illustrate the generating of an alternating current and voltage. On a graph, this produces a square-shaped wave. Waves of such abrupt characteristics are not common. The voltage produced by a simple AC generator or a vacuum tube oscillator follows this curve, as shown on an oscilloscope. It's called a sine wave. One complete swing above and below the time axis is called a cycle. Such a wave, generated along the time line by the gradual alternation of a point between positive and negative, is a curve which in its proportions is as common as the seasons of the year or the movement of ocean waves. It's the type of curve which describes the motion of a pendulum. It also describes the motion of the balance wheel of a watch. Since a sine wave involves such a gradual change of current, the sound made by a sine wave, as reproduced through a loudspeaker, has a musical quality. Waves of certain shapes are used in special applications. They include square waves and other odd shapes. Although they are seldom used to produce audible sounds, it's interesting to note how their sounds differ from those of sine waves. The normal sine wave, representing a voltage applied across an inductance, will be of the type shown in this graph. The current through an inductance in negligible resistance can also be pictured as a sine wave. And since the current in an inductance comes later than or lags the voltage producing it, the current sine wave reaches its peak values later than the voltage sine wave does. In a capacitive circuit, the voltage and current can be pictured as sine waves, but in this case, the current comes before or leads the voltage. This graph shows the sine waves representing the voltage and current in a circuit having resistance only. Notice that when there is zero voltage, there is zero current. When the voltage increases, so does the current. They keep right in step, or, as it's called, in phase. Now, if a small part of the resistance is removed and a small inductive reactance is substituted in its place, the entire current curve will move slightly to the right, showing that the current now lags the voltage, and the current and voltage are no longer in phase. The points of zero voltage and zero current no longer coincide. More resistance is now removed, and a comparable amount of inductive reactance is substituted. Finally, a point is reached where there is no resistance left, and inductive reactance alone displaces the current curve to its maximum distance to the right. Starting again with a purely resistive circuit, capacitive reactance is substituted for resistance. This displaces the current curve to the left, showing that the current now leads the voltage, so that they're no longer in phase. When the total opposition to current flow becomes capacitive reactance only, the curve reaches its maximum displacement to the left. Notice that when this occurs, the current is zero at the time the voltage is maximum. When the maximum inductive reactance is placed in the circuit and displaces the current curve all the way to the right, the current is also zero at the time the voltage is maximum. The curve has now been shifted toward the left. It indicates a circuit with capacitance and some resistance. If you wish to bring the current curve back in phase, one way to do it is to substitute more resistance for the capacitive reactance. There is also another method. Since inductive reactance tends to shift the curve in the opposite direction, the insertion of inductance in series with the capacitance will tend to balance the phase shift. A point of complete balance occurs when the amount of inductive reactance exactly equals the amount of capacitive reactance. At this point, the circuit behaves as though neither inductance nor capacitance were present, and as though there were only resistance in the circuit. This point is called resonance. Suppose you are working with this circuit and that you wish to calculate the voltage at the AC source. This coil, which is wound with heavy copper wire, has an inductance quality such as to produce 4 ohms of reactance at the AC frequency with which you are working. This resistance of 3 ohms is connected in series with it. Measuring the current with a special ammeter which reads maximum values, you find it to be exactly 1.0 amperes. If this were a DC circuit, the first step in calculating the voltage at the source would be to add together all of the series resistances to get a total value of R. Now, suppose that in this RL circuit, you add arithmetically the resistance and reactance. 4 ohms plus 3 ohms is 7 ohms. Substituting these values in the Ohm's law formula, you have E equals I times R, or E equals I times 7, or E equals 7 volts. Then, on checking the maximum value of the voltage drop across the inductance, you find a drop of 4 volts. Checking the voltage drop across the resistor, you find a drop of 3 volts. This makes a total drop of 7 volts and checks with your calculation. Now you measure the source voltage, expecting it to read 7 volts. But it reads 5 volts. Obviously, there must be a characteristic concerning AC to which DC formulas do not apply. An explanation of this will be given with the help of a drawing. First, consider two voltage curves, or sine waves, which are in phase. To add these sine waves, two corresponding parts of the curves may be taken. The voltage of this curve, as measured by the height, is 3 volts. The height, as shown by the dividers, indicates the instantaneous values of the curve. The second curve represents a value of 4 volts. The two curves can be added together by adding all their instantaneous values, and then plotting graphically the resulting values. By connecting these points, a new curve is derived, which is the sum of the first two. This is a graphic method of adding in-phase voltages and is as simple as adding DC. Out-of-phase voltages can be added by the same method. Here again is a 3-volt sine wave and a 4-volt wave. Since in this case the 4-volt wave represents a voltage drop across a pure inductance, it is displaced to the left, or leads the 3-volt wave, which is due to resistance alone. Here is a 3-volt peak. The 4-volt peak is of purely reactive nature, and therefore is displaced as you see it. Note that these values are the same as the voltage drops which were measured a few moments ago. Across the inductance, 4 volts. Across the resistance, 3 volts. Now the instantaneous values of the two curves are added as in the case of the in-phase components, and the resultant values are plotted on the graph. When these points are connected, a new curve is formed between the first two. Notice that the value of the new curve is not the direct sum of the other two, or 7 volts, but is 5 volts. This corresponds with the reading on the meter when the voltage source was measured. This graphic method is one way of determining source voltage when combining resistive and reactive voltages. It is possible to compare a complete voltage cycle with the complete revolution of a wheel. In other words, 360 degrees. This voltage curve, which may be due to the drop across a resistance, consists of one complete cycle. It occupies 360 degrees in the graph. Now a voltage due to an inductive reactance in series with the resistance is introduced. You will expect it to be displaced to the left the maximum amount, due to the reactance, or to the point at which the voltage due to the resistance alone is maximum at the time when the voltage due to the reactance is 0. As can be measured on the scale, this displacement amounts to exactly 90 degrees. Or you can say that the resistance voltage passes through 0 90 degrees after the inductance voltage goes through 0. In that respect, the inductive voltage leads the resistance voltage 90 degrees. Because of this 90-degree relation, you can use a geometric method of adding voltages in a circuit containing resistance and reactance. First, draw a straight horizontal line of a length representing one of the voltages to be added, say the voltage across the resistor. You may use any unit of measurement, centimeters, inches, or feet. This line is 3 units long and is labeled E sub R. It corresponds to the 3-volt drop across the resistor. The 4-volt drop across the reactance must also be considered. To represent the 4 volts, draw another line 4 units long. Notice that this is drawn at right angles, or 90 degrees, from one end of the first line. It is labeled E sub X. A 90-degree angle is used in this case because it corresponds to the 90-degree displacement between the 3-volt curve representing the drop across the resistor and the 4-volt curve representing the drop across the reactance. Now for the next step. Draw a straight line connecting the extremities of the two lines already drawn. This line is labeled E subtotal. Finally, measure the line just drawn. Its length, 5 units, corresponds to the measured voltage at the source. As before, the voltmeter indicates this voltage as being 5 volts. This is true even though the drop across the resistor is 3 volts, and though the drop across the reactance is 4 volts. You will recognize that the method of calculation used is that of Pythagoras, who many centuries ago proved that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. In the triangle just drawn, there have been represented the voltages across the resistance, the inductance, and the total of the two together. In a series circuit, of course, the same current must pass through all the components. You know from Ohm's law that the voltage across the resistance must be the current I times the resistance R. Likewise, the voltage across the inductance is the same current I times the reactance X. The voltage across the entire circuit is the current I times the total opposition of the circuit. This total opposition is called impedance and is designated by the letter Z. Now the hypotenuse of the triangle can be found as it was before, but using the new terms which have been substituted and which contain the circuit values. IZ squared equals IR squared plus IX squared. Then the i's can be taken out. And you have a triangle relating the resistance, reactance, and impedance. Therefore, in a series circuit of resistance and reactance, the impedance to alternating current may be found by the theorem of Pythagoras, just as the total voltage across the circuit can be found from the voltages across the parts of the circuit. In this impedance triangle, X is always drawn at right angles to R to represent the difference in phase between the voltages across the reactance and resistance. Since the effect of the inductive reactance is opposite to that of capacitive reactance, the impedance triangle for the latter may be drawn inverted. You will remember from the study of inductance that as the frequency is increased, the reactance increases. As the frequency increases, the reactance increases. From the study of capacitance, you will also remember that the greater the frequency, the less the capacitive reactance. Note that this graph is drawn below the horizontal axis. This is to indicate that the effect of capacitive reactance is opposite to that of inductive reactance, the graph of which was drawn above the axis. By combining the two curves, a frequency will be found at which the inductive reactance exactly equals the capacitive reactance. When this occurs with the inductance and capacitance in series with each other, the two balance each other, and a condition of resonance results. Series resonance, in this case, simply means that the reactive component of the circuit ceases to exist and the total impedance becomes equal to the resistance alone. If the frequency is changed ever so slightly higher, the inductive reactance component begins to predominate and the impedance rises. If the frequency is changed slightly lower, the capacitive reactance component begins to dominate and again the impedance rises. The farther from resonance the frequency is moved, the more one or the other of the reactive components predominates, and the higher the impedance becomes. Because it's the nature of capacitive reactance to increase at lower frequencies, capacity is the reactance which increases impedance at those frequencies. And since inductive reactance increases as the frequency increases, it is responsible for increase in impedance at higher frequencies. A graph can be drawn showing the series resonance in terms of impedance alone. Note that the value of impedance from A to B is lowest at resonance. Impedance never can be quite zero, however, because of small amounts of resistance always present in the best of circuit components. In the case of parallel circuits of inductance and capacitance, there are two possible paths for the alternating current to travel, either through the inductance or through the capacitance. Here again at low frequencies, the reactance of the inductor is very low. Since the inductor alone constitutes a complete path, the impedance from A to B also will be low at these frequencies. As the frequency is increased, the inductive reactance becomes greater, and the circuit impedance increases to its maximum amount at resonance. After the point of resonance of L and C, however, the bypass effect of the capacitor becomes evident, and as the frequency is further increased, the reactance of the capacitor decreases, and the circuit impedance drops lower and lower. Resonance may be defined in two ways. First, resonance is the frequency at which inductive and capacitive reactances are equal. Second, the resonant frequency is a point in a series combination of L and C where the impedance due to their combined reactance is minimum. And in a parallel combination, it is a point where the impedance is maximum. The effect of high or low impedance at resonance may be illustrated in many ways. For instance, my voice has been recorded on film in such a manner that all frequencies from 30 to 10,000 cycles are given equal emphasis, or, as it is commonly expressed, response. But if somewhere across the recording circuit there is inserted a series L and C combination, resonant at 1,000 cycles, the impedance at that frequency will be low enough to partially short-circuit my voice at frequencies in the vicinity of 1,000 cycles. When the switch is closed, there is a noticeable change in the quality of my voice. The response curve shows why this happens. It is due to the filtering out of frequencies in the vicinity of 1,000 cycles. When the switch is open, my voice sounds normal again. In a similar way, there might be inserted across the circuit a parallel combination of C and L, also tuned to 1,000 cycles. This combination presents a high impedance near resonance and a low impedance at all other frequencies. When the switch is closed, which controls this combination of C and L, a totally different quality of voice reproduction is evident. This is because all frequencies except those in the vicinity of resonance are dissipated. The net response then is only a very narrow band of frequencies around 1,000 cycles, producing a quality not unlike the early telephone. It is in marked contrast to the response curve normally used for modern reproduction of sound with motion pictures. Combinations of R, C, and L used in such a manner are called filters and may take the form of equalizers, compensators, tone controls, and noise filters. A very important use for parallel resonant RCL combinations is the so-called tuned circuit used in radio transmission and reception. Since the reactance values of C and L determine the resonant frequency, it is obvious that by varying the values of either C or L, the resonant frequency will be changed. In tuning a radio receiver, L usually remains constant, and the value of C is changed. In general, the maximum practical change in capacitance with a given inductance will allow a change in resonant frequency in a ratio of 3:1, or in the case of a broadcast receiver, from 550 kilocycles to 1500 kilocycles.